Yo, what's up, everyone? Welcome to the start of Oxidation Reduction. And welcome to Oxidation Reduction Part 1. Today we're going to be talking about oxidation numbers, and we're also going to introduce the galvanic cell. So let's get into it. So basically, this entire unit is about electrochemistry. And electrochemistry is just the study of the relationship between chemical reactions and electricity. Electricity is kind of confusing sometimes. So what is electricity? Well, electricity is just the flow of electrons. And the way we can relate chemical reactions and electricity is if we look at redox reactions. So if we look at this net ionic equation of a redox reaction right here, you'll notice that we can split this up into two half reactions. The one including the iron and the one including the cesium. And you can see in one of them, an electron is produced, and then in another one, the electron is used up again. That is simply just a redox reaction. A redox reaction is just when one half cell or one half reaction produces an electron, and the other half reaction just uses it back up. So we call the reaction involving the iron the oxidation half reaction, and we call the one with the cesium the reduction half reaction. I think I've been calling it cesium. It's apparently cerium. Whoops. But essentially, a reduction half reaction is called a reduction even though it gains an electron because the electron reduces the charge of the atom. So it started off with cerium 4 plus and it gained an electron, so it decreased its charge value to 3 plus. And that oxidation is increase in charge, but you lose an electron. And once you add up these two half reactions, you get the equation that you were starting off with. So if you add all them up, the electrons cancel out, and you are just left with the final redox reaction. So if you were to draw this out, you could have something like the iron 2 plus is transferring an electron to the cerium 4 plus. But the thing is, that little flow, that little transfer, is simply just a flow of electrons. All we would have to do is, put a line between the iron and the cerium in order to create a longer flow of electrons, and that's simply just electricity. We're creating electricity using redox reactions. So in electrochemistry, it's really important to know which substance is getting oxidized and which one is getting reduced. And the way we do that is using oxidation numbers. And we've already covered oxidation numbers, but I want to quickly go over it. These are just a chart of the rules of oxidation numbers. And so let's just do a little practice with it. So find the average oxidation state of tin in this big chemical formula here. Since we've already kind of done this before, I'm kind of going to speed over it. So we know that the final charge of this entire thing is going to be 0. We know that oxygen has a -2 oxidation number almost always, so we can add that. So 6 times -2. OH is a monatomic or a polyatomic ion, and it has a charge of -1. So let's add that charge. Chloride is a monatomic ion. It has a charge of -1. So we have 16 times -1. And if we add all this up, so -12 plus -32, so we have -44. We know that the 21 tin is going to have to, the charge of the 21 tin is going to have to equal 44. So if we have 21 of them, how much are each going to have? What's the oxidation number of each? Well, it's just going to be +2. And that's the only way the entire chemical formula gets an oxidation number of just 0. So the average oxidation state of tin is 2, and that is the right answer. Okay, so an apparatus that takes advantage of these redox reactions is something known as a galvanic or a voltaic cell. So this is just a mechanism that leverages redox reactions to produce electrical energy. And you're definitely familiar with galvanic cells because a type of galvanic cell is a battery. So the batteries that are charging your phones, your computers, anything. You've likely experienced a galvanic cell every day of your life for the last 5 years. So how do they work? Imagine you have this redox reaction where zinc and copper sulfate are reacting to create zinc sulfate and copper solid. What would happen is that you would first write the net ionic equation and then divide them into their oxidation and their reduction half reaction. Now from here, if we were to separate the oxidation half from the reduction half in some way, and we just put a line through them, what we'd have is a transfer of electrons. Remember, in this oxidation cell here, you are producing the electrons, and they're going to go to this reduction half cell. So as long as we are able to figure out what goes into each of these and just put a line through them to facilitate the flow of electrons, we are producing a galvanic cell. And so we've been really ambiguous about what's actually in these cells. So let's go a bit deeper into what is inside one of these particular cells. So first of all, you have your oxidation half and your reduction half, and they're all always going to be in some aqueous solution. We'll go through what that aqueous solution is exactly, but the reason we use an aqueous solution is because electricity flows through aqueous solutions, and it also helps us standardize the solution for when we need to make measurements. So the first thing that we're going to have is a zinc solid and a copper solid on each half cell. And they're going to be connected using this wire. And that wire is what's going to facilitate the flow of electrons. All right, we have that solid. What about the aqueous bit? Well, in the aqueous bit, you're going to have zinc sulfate and copper sulfate. So ZnSO4, and you're going to have copper SO4. Again, this is so that the electrons are free to move and so that you create a standardized solution for when we need to measure something known as cell potential, which we'll go over more in the next video. And remember, throughout this whole process, there is electrons flowing through this line. So if you were to, set up a light bulb there, the light bulb would actually turn on. Electricity is just a flow of electrons, and light bulbs need electricity. So this is the main bit of the galvanic cell. So let's see how the oxidation and reduction equations are going to affect the cell. So look at the oxidation half equation. What we realize is that zinc solid gets used up to produce zinc ions and 2 electrons. What this means for this oxidation half here is that the zinc is going to start to deteriorate. As more and more zinc get used up, the shape is going to become smaller and the mass is going to become smaller of this zinc solid here. On the other hand, if we look at the reduction half, copper solid is being produced. So over time, the copper solid is also going to change shape, except in opposite of the zinc, the copper is actually going to gain mass. So it might just get a little bigger here or whatever. But there's another thing that's happening in these oxidation and reduction half cells, and it's the buildup of different charges. So what do I mean by that? Well, in the oxidation half, zinc is being produced, and that zinc has a +2 charge. Now, as we add more zinc ions here, what you'll realize is that this oxidation half cell is going to get it's going to build up positive charge. And since the sulfate ions stay the same, you don't have those negative charges to balance out that positive charge. On the other hand, in the reduction half, you realize that the copper ions are being used up. And so as you use up more and more copper ions, what happens is that you have a buildup of negative charges. And so when you have galvanic cells with a overwhelming amount of positive and negative charges, when you have that charge imbalance, the galvanic cell ceases to work at a certain point. So what's the solution here? Well, it's something known as a salt bridge. In a salt bridge, you usually have this U-tube. And in this U-tube, you have some sort of salt. And in this case, we have NaCl. But you might see something like, I don't know, potassium chloride or really any other salt. And the function of this salt bridge is to distribute ions to each half cell. So what do I mean? Remember, a overabundance of positive charges are going to start building up on the oxidation half. And since we have that, we're going to need negative charges to balance that out. What's going to happen over time is that the chloride ions are going to start to migrate to this side and go into the cell here. On the other hand, we have a buildup of negative charges on the reduction half cell. So sodium ions are going to start migrating to this side of the U-tube. At the end of these U-tube, we have usually like a cotton plug here. And that cotton plug makes sure that the entire solution just doesn't pour out into the half cells, so that we have a facilitated transfer of ions, so that we can have a balance of charge in the oxidation and reduction half cell. I've been calling these the oxidation and reduction half cell, but these guys actually have names. And the oxidation half cell is known as the anode, and the reduction half cell is known as the cathode. I guess the memorization trick I use is just I remember an ox and a red cat. I think I made this up. I don't think I saw this anywhere, but for some reason it just helps me remember it. So an represents anode, anode is ox, ox represents oxidation, and then we have red. Red stands for reduction, and then cat stands for cathode. It helps me. If you want to make up your own one, then yeah, feel free to do so. Just use whatever helps you memorize it. So again, the anatomy of a galvanic cell is a solid, and then a solid on this half too, and it's submerged in some ions here. And in this case, we have a zinc sulfate solution and a copper sulfate solution. And over time, that oxidation and reduction reaction happens, so the solid on the oxidation half starts to deteriorate, and the solid on the reduction half starts to grow in size. But we also have this charge imbalance that builds up, so we need a salt bridge to mitigate those charge imbalances. One last thing about galvanic cells for now is something known as cell notation. So when making a galvanic cells, it's really helpful to have some notation so that we don't have to keep drawing out these diagrams. We can just have the cell notation tell us what's in the anode, what's in the cathode, and we can just use that to do experiments, or we can use that to solve problems. So what are the rules for cell notation? Well, first of all, anode components go on the left and cathode components go on the right, and those anode cathode components are separated by this double, what is this, double vertical line here? That double vertical line. So what does that mean? So we know it's going to be separated by some double vertical line, and we know that the anode components go on the left and the cathode components go on the right. All right, let's keep reading. So phase changes within the anode slash cathode are separated by a single vertical line, and same phase components in anode cathode are separated by comma. All right, so let me just do an example here so that you understand how to write cell notation for this particular galvanic cell. So remember, our anode is going to have the zinc solid, and it's also going to have the zinc 2 plus aqueous. We're not going to include the sulfate ion because, frankly, it's really not important. If you look at the half reactions or the entire full redox reaction, the sulfate really is not important. The only thing important are those ions and the solid. So in the anode, we have these. So let's just write them. So we have zinc, solid, but remember, we're changing phases. We're going from solid to aqueous, so we need the single vertical line. That single vertical line represents a phase shift, and so the other component would be this. And now we have to do the same thing for the cathode. In the cathode, we have our copper solid, but we also have our copper 2 plus aqueous. And so we can write that here. We can have copper 2 plus aqueous. And since we have a phase shift, we have to include one vertical line, and then we write our copper solid. And simply that's just our cell notation for this galvanic cell. If we didn't have a phase shift, then we would just use a comma instead of that single vertical line here. All right, that's all I have for this lesson. I hope you were able to learn something, and I hope to see you later for part 2. Thank you for watching.